For generations, the study of polar ice sheets was governed by the physics of deep time. We measured changes in centuries, projecting the slow, majestic retreat of glaciers across generations. But in the Amundsen Sea sector of West Antarctica, that temporal scale has abruptly collapsed. Scientists studying the largest ice mass on Earth have retired their long-term forecasts and replaced them with a timeline measured in years, months, and days. The floating shelf holding back the planet's most dangerous glacier is undergoing rapid, systemic structural failure, and researchers warn its complete disintegration could occur any day now. The subject of this crisis is the Thwaites Eastern Ice Shelf. It is a floating slab of ice roughly 350 meters thick that extends over the open ocean. For as long as observations have existed, this shelf has performed a singular, critical mechanical function. It acts as a structural buttress, a literal cork wedged into a bottle pressing back against the massive grounded glacier behind it. That glacier is Thwaites. Known to researchers as the Doomsday Glacier, it is the widest glacier on Earth, stretching 120 kilometers across the Antarctic coastline, an area roughly equivalent to the size of Great Britain or the state of Florida, and reaching a thickness of nearly 2 kilometers. To understand the scale of the structural deficit, one must analyze the mechanical relationship between these two bodies. A floating ice shelf only 350 meters thick is responsible for restraining an inland ice mass more than 5 times its own thickness. More alarming still is how this massive buttress is anchored. The entire Thwaites Eastern Ice Shelf is held in place by a single highly vulnerable point of contact. Deep beneath the ocean surface, a submarine ridge rises from the seafloor, and the underside of the floating ice catches against it like a fingernail hooked on a ledge. A single isolated geological anchor is carrying a dynamic load equivalent to an entire country. This is not a theoretical model or a simulation. The imminent failure of this anchor has been meticulously documented. In a comprehensive study that compiled 20 years of data spanning from 2002 to 2022, researchers combined satellite observations, precise ice flow velocity measurements, and GPS instruments installed directly onto the ice surface. This 2-decade time-lapse revealed that the shelf is tearing itself apart from the inside. The damage is concentrated in the shear zone, the highly stressed seam where the active ice shelf grinds against slower, stagnant ice and rock at its margins. Over 20 years, cracks have grown steadily, tracing a pattern of progressive mechanical detachment. Today, the shelf is heavily fractured, laced with deep fissures, and visibly pulling away from the grounded glacier. The empirical consensus has grown remarkably sharp. A pivotal study published in 2025 concluded that this vital structural barrier is likely to shatter within the next 5 years. Marine geophysicists, including Robert Larter of the British Antarctic Survey, have narrowed that window even further, stating that the breakup is highly likely to occur as early as 2026. To evaluate this transition accurately, we must separate the immediate physical event from its long-term consequence. Because the Thwaites Eastern Ice Shelf is already floating, its physical disintegration will not raise global sea levels overnight. Much like an ice cube melting in a glass of water, the floating ice has already displaced its own weight. The shattering of the shelf itself is not the disaster. The shattering of the shelf is the starting gun. The true systemic threat lies in the elimination of the frictional drag. Once this marine barrier is removed, the enormous grounded glacier behind it, resting on bedrock far below sea level, will lose its primary break. Free from restraint, the massive inland ice sheet will begin to accelerate its march toward the ocean, initiating a multi-century process of committed sea level rise that cannot be halted. The mechanical driver of this failure is not atmospheric. It is a subsurface assault. Deep beneath the freezing surface waters of the Southern Ocean lies a dense, salty, and relatively warm water mass. Guided by deep seafloor topography, this warm water penetrates deep into the subglacial basins of West Antarctica, flowing directly beneath the floating ice. It is eating away at the single pinning point from below, melting the ice at the exact interface where it grips the seafloor ridge. The ocean has absorbed roughly 90% of the excess heat trapped by greenhouse gases across 70% of the Earth's surface. And that thermal energy is now being delivered directly to the structural foundations of Antarctica. This brings us to the fundamental geographic vulnerability of the West Antarctic ice sheet, a reality that remained hidden until the release of the Bedmap 3 project in 2025. By synthesizing 60 years of data, 84 airborne radar surveys, and over 52 million measurement points, Bedmap 3 revealed a stark geological division. While East Antarctica sits on solid rock safely elevated above the ocean, West Antarctica is structured as a series of deep basins plunging far below sea level. Thwaites Glacier sits in the deepest, most vulnerable basin of them all. The stage is set. The structural cork is fracturing, its submarine anchor is being melted away by deep ocean currents, and the country-sized glacier behind it sits in a deep marine basin that slopes downward into the interior of the continent. If the Thwaites Eastern Ice Shelf fails, we are not just losing a block of ice, we are unlocking the gate to a vast, unstable marine basin. Which raises the ultimate question: once the gatekeeper steps aside, what physical mechanisms prevent the entire West Antarctic ice sheet from sliding into the sea? To find the answer, we must examine the specific physical feedback loop that defines the West Antarctic ice sheet: marine ice sheet instability. When the bedrock beneath the glacier slopes downward as it moves inland, the boundary where the ice lifts off the ground and begins to float, the grounding line, is forced into deeper water. In deep water, thicker ice is discharged at a much faster rate. This rapid discharge drags the grounding line further back into still deeper basins, which in turn increases the ice thickness at the boundary and accelerates the discharge even more. This is not a linear retreat. It is a self-sustaining runaway loop. Once this threshold is crossed, there are no mechanical brakes left to apply. Satellite measurements already show this process in action, with thinning extending 100 kilometers inland along the glacier's deepest trough. But Thwaites does not exist in isolation. It is the keystone of the entire Amundsen Sea sector. In the physics of structural arches, the removal of the central stone does not merely damage the apex, it causes the entire span to collapse. Thwaites serves as the gatekeeper for neighboring giants like the Pine Island Glacier, which is already among the fastest changing ice masses on Earth. If Thwaites retreats beyond its critical threshold, the structural support for these adjacent glaciers is eliminated, allowing them to flow unchecked into the ocean. The quantitative reality of this scenario was laid bare in March of 2026. A study led by the researcher Goldberg utilized two independent ice sheet models, calibrated against real-world observations from 2004 to 2017, to project the glacier's behavior to the year 2067. The results are stark. By the 2060s, Thwaites alone is projected to lose between 180 and 200 billion tons of ice annually. To appreciate that scale, that single glacier's annual loss will equal the total mass currently lost by the entire Antarctic continent today. Crucially, the study revealed a sobering methodological truth. The models that most accurately simulated the observed historical behavior of Thwaites were the exact same models that projected the highest, most severe ice losses. The worst-case scenarios are not outliers generated by faulty assumptions. They are the most mathematically sound projections we have. This empirical precision directly refutes the common dismissals of polar science. Some argue that these models are speculative exaggerations, yet they are graded against 20 years of hard observed physical data. Others claim this is merely part of a natural cycle. While Antarctica has indeed fluctuated over geological epochs, the rapid rate of contemporary change and the specific mechanism of warm water undermining the ice from below conforms to ocean warming, not natural orbital rhythms. The global sea level budget confirms this transition. From 1960 to the early 2000s, global sea level rose at an average rate of 2 millimeters per year. Between 2005 and 2023, that rate nearly doubled to approximately 4 millimeters per year. Driven increasingly by melting land ice rather than simple thermal expansion, equally untenable are conspiratorial narratives suggesting this melt is being engineered by targeted weather technologies. A basic calculation of the planetary energy budget exposes the absurdity of this claim. The heat driving this retreat is not a localized force. It is the product of global oceans absorbing 90% of the excess energy trapped by greenhouse gases across 70% of the planet's surface. The thermal energy required to destabilize an ice shelf of this magnitude is orders of magnitude beyond any human technology. The culprit is diffuse systemic warming, not a localized beam. The physical numbers translate directly into human geography. Thwaites Glacier contains enough ice to raise global sea levels by 65 centimeters. If its collapse triggers the wider destabilization of the West Antarctic ice sheet, the total potential rise reaches roughly 3 meters, or 10 feet. Such an increase is not a distant abstraction. It is a physical force that would displace between 500 million and 1 billion people worldwide. The impact zones are the economic and cultural hubs of modern civilization: London, New York, Miami, Shanghai, Tokyo, and the vast low-lying deltas of Bangladesh, where millions live within feet of the high tide line. The collapse will not happen overnight. It will unfold over decades and centuries due to the immense physical inertia of the ice. But the loss of the Thwaites Eastern Ice Shelf will be the definitive turning point. When the announcement comes that this outer barrier has shattered, no immediate wall of water will hit our shores. Instead, it will mark the quiet, irreversible moment we unlock the gate to a rising ocean. The technological effort to map this systemic vulnerability has revealed a profound scientific paradox. As our observational instruments have grown more precise, the projected outlook has grown demonstrably worse. Historically, researchers expected that finer resolution would narrow margins of error, potentially smoothing out the most extreme scenarios. The reality has been the exact opposite. With the implementation of advanced tools like the Polar RES Climate Dataset, which integrates 4 state-of-the-art regional climate models at an unprecedented 11-kilometer resolution specifically tuned for Antarctic coastal weather, we have not found reassurance. Instead, every increase in resolution has unmasked previously hidden subglacial basins lying deep below sea level and mapped entirely new pathways for ocean water intrusion. Sharper instruments did not calm the picture. They merely exposed a far more unstable subterranean network than legacy models had assumed. This high-resolution modeling directly feeds into our understanding of the ocean's changing mass balance. For decades, the primary driver of global sea level rise was thermal expansion, the physical reality of water expanding as it warms. A long-term global budget study shows that thermal expansion accounts for roughly 43% of the total sea level rise observed over the past 60 years. However, the internal mechanics of the global climate engine shifted decisively in the 1990s. Since that decade, the melting of land-based ice sheets has bypassed thermal expansion to become the single fastest-growing contributor to rising oceans. This transition represents a fundamental phase change in the planetary system, moving from a warming fluid dynamic to the physical liquidation of massive terrestrial ice reserves. The mechanisms of this liquidation remain shielded from direct human sight, occurring kilometers beneath the ice where the deep ocean meets the continental bedrock. Because this destruction is invisible, it has become fertile ground for alternative narratives. Critics often question why, if the threat is so severe, it does not dominate daily headlines. The explanation lies in the mismatch between human information cycles and geophysical timescales. The news cycle is optimized for immediate discrete events, whereas the disintegration of an ice sheet is a slow-motion structural collapse unfolding over decades. There is no single, catastrophic frame to capture on camera today. The science itself is entirely public, openly published in peer-reviewed journals for any analyst to verify. Furthermore, the scale of this thermal transfer dismantles any suggestion of localized or artificial intervention. To melt ice sheets of this volume requires an energy budget that defies human engineering. The planetary ocean, covering more than 70% of the Earth's surface, acts as the primary heat sink for the global climate system, absorbing approximately 90% of the excess energy trapped by greenhouse gases. This colossal volume of heat is transported by global current systems, driving the deep, warm, salty water mass directly into the subglacial troughs of the Amundsen Sea. This is not a targeted beam, it is a planet-scale redistribution of thermodynamic energy. This planetary scale brings us back to the human coastlines. The physical reality of a 3-meter sea level rise forces a choice between two distinct futures. The first is an orderly, planned, and multi-trillion-dollar engineering retreat. This would require constructing coastal defenses and systematically relocating critical infrastructure in megacities like London, New York, Tokyo, and Shanghai over several generations. The second path is chaotic, unmanaged displacement, where sudden coastal failures overwhelm regional economies, forcing up to 1 billion people to migrate inland as tides permanently reclaim low-lying nations like Bangladesh. The ice of West Antarctica operates under the strict and different laws of thermodynamics and gravity. It possesses massive physical inertia, which prevents it from emptying into the sea overnight, but it also means that once the structural breaks are removed, the momentum cannot be reversed. The upcoming fracturing of the Thwaites Eastern Ice Shelf is not just an isolated environmental event. It is the mechanical release of the planetary lock. When that floating buttress shatters, the physical boundary conditions of our global coastlines will be permanently altered, leaving us to navigate the slow, inexorable rise of a new ocean. The systematic collapse of the Thwaites Eastern Ice Shelf is not an isolated event of local interest, but the primary catalyst in a global chain reaction. To fully comprehend the gravity of this transition, we must synthesize the 4 independent lines of evidence published within about a year of each other, which now point in the same direction. These are not disparate observations but interconnecting layers of a singular, highly verified geophysical diagnosis. The tools are only getting sharper, and their combined output leaves no room for speculative alternative interpretations. The first pillar is the bedrock topography mapped by Bedmap 3, which exposes the deep basins and subglacial pathways of West Antarctica. This bedrock geometry acts as a physical funnel, allowing deep, warm, salty ocean currents to penetrate kilometers inland beneath the ice sheet. This is the structural vulnerability that initiates the entire crisis, exposing the glacier's anchoring zones to constant thermal erosion. The second pillar is the 20-year fracture study spanning from 2002 to 2022. By tracking the propagation of fissures through the shear zone frame by frame, this research proved that the shelf is not experiencing a sudden unexpected failure, but a steady decades-long slide toward complete structural detachment. The cracks running through the very seams that hold the shelf to its submarine pinning point have systematically weakened its grip, bringing the structure to the absolute limit of its mechanical load. The third pillar is the global sea level record itself. The hard data confirms a profound shift in the planetary water budget. While thermal expansion of warming ocean waters historically dominated sea level rise, melting land ice has emerged since the 1990s as the fastest growing driver. This is accompanied by an observed doubling in the rate of global sea level rise, climbing from an average of 2 millimeters per year since 1960 to approximately 4 millimeters per year between 2005 and 2023. This acceleration is the direct physical consequence of polar ice sheets discharging their mass into the ocean. The fourth and final pillar is the state-of-the-art ice sheet modeling. When 2 independent models, built by different methods and calibrated against the actual changes observed at Thwaites between 2004 and 2017, were projected forward to the year 2067, they yielded a deeply unsettling agreement. They warned that Thwaites alone could reach annual ice losses of up to 200 billion tons per year by the mid-century. Crucially, the models that best matched the actual historical observations were the exact models projecting the most severe future losses. This means the loudest alarms are coming from our most reliable, highly verified tools. These 4 lines of evidence form a cohesive, indisputable picture. The bedrock map shows the terrain that lets the warm water in, the fracture study shows the shelf's progressive slide toward failure, the sea level record confirms that melting land ice is already accelerating the rise, and the ice sheet models project the compounding consequences of this runaway feedback loop. There is no single component of this system that can be dismissed as an anomaly. The global ocean serves as the physical transmission line that connects the remote, frozen basins of West Antarctica directly to the doorsteps of human civilization. A crack in a floating slab of ice at the bottom of the world is not a distant curiosity. It is a direct alteration of the hydrostatic pressure acting against every seawall, port, and coastal community on the planet. The physical distance between Antarctica and our major urban centers is a geographic illusion. The water that currently braces the Thwaites Glacier will eventually become the water that floods the low-lying streets of London, New York, Tokyo, and Shanghai, and permanently displaces millions across the coastal plains of Bangladesh. This is the reality of a planet operating under the strict, indifferent laws of thermodynamics. The heat has been absorbed, the ice is responding, and the structural limits of the system have been reached. The upcoming breakup of the Thwaites Eastern Ice Shelf is the definitive physical threshold. It is the moment the brakes are removed, initiating a century-scale transition toward a higher global ocean. The science is clear, the mechanism is active, and the timeline is no longer a matter of the distant future. It is a reality we must confront today. As we trace this chain reaction to its ultimate destination, we must confront the strict physical boundaries that govern the global climate engine. The collapse of the Thwaites Eastern Ice Shelf is the final mechanical step before the unchecked acceleration of the glacier itself. When this floating cork is removed, the physical barrier that has held back the West Antarctic ice sheet for millennia will cease to exist. This is the structural limit of the system, a threshold where the balance of forces shifts irreversibly from stability to rapid, self-sustaining discharge. The numbers are clear, and they define the scale of the challenge ahead. Thwaites Glacier by itself contains enough ice to raise global sea level by 65 centimeters. But because Thwaites acts as the keystone holding the surrounding ice sheets in place, its collapse could trigger the wider destabilization of the West Antarctic ice sheet, which holds a potential 3 meters of sea level rise. This is close to 10 feet of ocean added to every coastline on Earth. This is not a speculative scenario, it is a physical commitment, once the grounding line retreats past the submarine ridge. The laws of gravity and ice dynamics dictate that the ice must flow toward the sea. This physical reality directly dismantles the superficial narrative that humanity can easily engineer a solution to this crisis once it begins. The sheer scale of the energy budget involved exposes the limitation of human technology. To halt the retreat of a marine ice sheet that is being undermined by a warming global ocean would require redirecting ocean currents and cooling millions of cubic kilometers of water. The thermal energy currently melting the pinning point from below is not a localized phenomenon that can be blocked. It is the accumulated heat of 90% of the excess energy trapped across 70% of the planet's surface. The system is operating on a scale that dwarfs any engineered intervention. This brings us to the ultimate human factor, the rate at which we can adapt to a changing planet. Coastal researchers estimate that a 3-meter sea level rise is enough to displace between 500 million and 1 billion people. This is not a distant problem for future generations. The acceleration has already begun. The global average rate of sea level rise has doubled from 2 millimeters per year since 1960 to 4 millimeters per year between 2005 and 2023. This doubling is the direct physical signal of land ice entering the ocean. The timeline is compressing, and the window for orderly adaptation is shrinking. The choices we make in the coming decades will determine whether this transition plays out as a planned, manageable relocation of coastal cities or as a series of catastrophic failures. The ice sheet does not care about political cycles, economic projections, or human timelines. It responds only to the physical laws of thermodynamics and gravity. The heat has already been absorbed, the fractures have been documented over 2 decades of observations, and the submarine ridge that has anchored the shelf is losing its grip. We are standing at the edge of a profound geographic transition. The upcoming shattering of the Thwaites Eastern Ice Shelf will not cause the oceans to rise overnight, but it will mark the quiet, irreversible moment the break was removed from the most dangerous glacier on Earth. The 4 independent lines of evidence, the bedrock mapping of Bedmap 3, the 20-year fracture study, the rising global sea level record, and the consensus of the ice sheet models, all point to the same conclusion. The structural limit has been reached. Antarctica may feel like a remote, frozen wasteland, completely detached from our daily lives. But the global ocean is the great connector, linking the ice at the bottom of the world directly to our coastlines. A crack in a slab of ice in the Southern Ocean is a direct threat to the stability of human civilization. As the shelf pulls away from its last anchoring point, it serves as a stark reminder of the hard limits of the natural systems that sustain us. The question is no longer whether the system will change, but whether we will recognize the signal before the gate is opened.